We're going to look at two different ways that the nucleus of an atom can decay. So this is just supposed to represent the nucleus of an atom. We've got protons, we've got neutrons in here. I'm not making any sort of effort to actually represent a specific atom. This is just a large atomic nucleus. So at some point, the instability of this atom will manifest itself with one of two different kinds of ejection of material. The first way this can happen is the actual ejection of two protons and two neutrons. Those are supposed to be protons and then neutrons. So this entire thing is ejected from the nucleus, and so the nucleus itself loses two protons and two neutrons. You might recognize this as the nucleus of a helium atom, so we sometimes call it a helium nucleus. More often it's just called an alpha particle. An alpha particle is, in fact, just a helium nucleus. It's two protons and two neutrons. So when this nucleus ejects this material, notice that the atomic number of this atom has to change, which means that this atom has to change into a different atom. The atomic number decreases and by 2. We would say that the nucleon number, that's the number of particles in the nucleus, decreases by 4, right? We've lost 4 things. So as an example, pull up my periodic table here. If we have uranium with atomic number 92, if uranium decays by an alpha process, it turns into thorium with atomic number 90. All right, we've lost 2 protons. We've also lost 2 neutrons. That's not reflected in the atomic number, but we do have something called the nucleon number, which will decrease by 4. But usually what we care about is the atomic number, because that actually tells us what element it is. So uranium then decays into thorium is how we would say that. That is a nuclear decay process, and in the course of that decay releases this high energy alpha particle. So if you've ever wondered where the energy comes from in nuclear energy production, it's here. This carries away a large amount of kinetic energy. If you really want to get into nuclear power, it's really, really fascinating. What happens is part of the mass of all of this stuff is converted into the kinetic energy of this particle in accordance with the famous equation E equals mc squared, the mass energy equivalence. If you're really interested in that, I would encourage you to read your textbook. We're not getting into that that far in this course. What I do want you to be familiar with, though, is this type of radiation, this alpha particle. But the kinetic energy of the particle is then you can transfer that energy into heat of water, which you can then boil and use steam to turn a turbine. That's the source of nuclear energy. Actually, it's the kinetic energy of particles like this. That's one process. This is an alpha process. There is another process called the beta process, which produces the beta particle. Turns out the beta particle is just an electron. And I should say this is a very crude assessment of the beta process. There are also things called neutrinos that get produced here. For the purposes of this course, though, we're just concerned about the electron. If you are in some sort of nuclear or atomic physics course or engineering course, this is way below the level that you would probably need for your class. But for my class, which is just a brief introduction to these processes, this is going to be just fine. This is a beta process, just an electron, or in this context, very often called a beta particle. This is produced in the nucleus, and I say produced because it's actually produced. It's not that there was an electron hanging out in the nucleus and then it just decided to leave. This is actually produced in the decay process. So there were no electrons in the nucleus, and then all of a sudden there's one flying away from the nucleus. What happens? Well, what happens is one of the neutrons decays into a proton, and it's not an electron, but it's got the fundamental charge and an electron. So the number of protons in the nucleus has increased by 1. The number of nucleons hasn't changed, but the atomic number increases by 1. The nucleon number is the same, because one of my nucleons, which was a neutron, has now become a proton. It becomes a proton by releasing this electron, which then flies out of the nucleus at high energy, again able to be captured and turned into energy if you so desire. But this is the beta process. As an example, let's go back to uranium, which has an atomic number of 92. If uranium happens to decay with a beta process, it turns into neptunium, which is atomic number 93. So in both cases, we decay into another element. In both cases, what we decay in these particular examples, the element we decay into is also unstable and will decay further. Which of these processes happens depends on the element. It depends on the conditions. It depends on which isotope of the element is. There are certain elements which only have one of these processes available to it to decay. There are certain elements which can decay through, and I should say certain isotopes which can decay through either of these processes. If you're interested in the details of that, there are some charts in your book that show you what happens, but that is not something you will need to know for my class. What you do need to know are these processes, what they mean, and how the changes work between elements. An alpha decay process results in a decrease of atomic number by 2. A beta decay process results in an increase of atomic number by 1.